Good afternoon. I'm Denise Edwards. I am a research staff member here at the Institute for Defensive Analyses in the Operational Evaluation Division. I'm the speed session chair today. I'm also like a bouncer today. So each of our speakers are going to have 9 minutes to give their talk. And if they leave a little room for a question, maybe two at the end, that's on them. But, just to, keep us on track and, respect everyone's time. Just so you know, when you get close to the end, I'm going to stand up. And, I do work out. So if I start walking towards you, be ready. Okay. So thank you all for joining us today. Our first presenter is Andrew Cooper, who is a fourth-year PhD student at Virginia Tech.
Thanks. Hey, everyone. Yep, so my project is called Data-Driven Robust Design for an Aeroelastic Wing. This is work I did in collaboration with Luis Crespo and Brett Stanford over at NASA's Langley Research Center. Okay, so usually when I go to talks like this, there's at most one thing I kind of remember after leaving because there's just so many talks going on. So I thought I'd just tell you if there's one takeaway from this presentation, it's that identifying robust designs with simulators is a challenging task, but Bayesian optimization methods can be an effective approach. Okay, so here's kind of this wing design problem as kind of our motivating problem. So researchers are often interested in evaluating unique wing designs. So one common goal for researchers is you want to find a wing design that minimizes weight, but it doesn't flutter too much. And right, these are competing objectives. So wing behavior depends on a ton of very complex aeroelastic properties, a lot of which I don't understand, right, which can make it difficult. So if you want to do an optimization process, this could be a challenge. So especially because field experiments can be very costly and time intensive if you want to do that. So one way to get around that is that researchers build simulators, right? They put in all the kind of equations and models to simulate a wing mid-flight and how it would behave. So right, so just kind of the one equation I have in my presentation is you have a black box F, you give it an input X, you have some error associated with it, maybe some noise, and then you get some output Y. One issue is this can still take a while to run, right? This is, these simulators, even with high-powered computing, can take a while. And this could be a problem if you're doing some kind of optimization task where you need to evaluate the gradients, you need to evaluate the simulator a bunch of times. It can be very costly. So what's one way to kind of get around this? What's one approach? So I'm going to talk about something called surrogate modeling. So surrogate models are statistical models that mimic simulators. So here's kind of a simulated example that shows you have two inputs and one output. I did two inputs because it looks nice because you can make these nice 2D visuals. So basically what you do is you collect some data, some training data. In this case, this is from a Latin hypercube design, a space-filling design. And you fit a model that gives you a prediction at new locations, right? And what's key about this surrogate models is that they're thrifty. They're quick to evaluate compared to a simulator. And since it's a prediction, you want to give some sort of uncertainty quantification to it. So you basically estimate how sure you are of your estimate. And it makes sense that the farther you are away from training points, the more unsure of your estimate you are. Okay, so how do we use a surrogate optimization, right? Going back to the original problem. Our goal is to minimize the weight of a wing, right? I'm going to take the flutter thing out of the equation just for a second. So how do we use surrogate models to find an optimal wing design? So I'm going to talk about this sequential design algorithm that's known as Bayesian Optimization. So I'm going to take you through it. Okay, using the same simulated example, 2D example, here's what I'm going to do. I'm going to first generate just an initial design of a few points, just really the minimum needed to fit a model, a surrogate model. Right, so this is, again, a Latin hypercube design. I fit my surrogate. Doesn't matter what surrogate. I'm using a Gaussian process if you're interested. So I fit my surrogate model. I generate a candidate set. Basically, it is another space-filling design where I'm going to pick one of these points to actually acquire. And so how do I pick which of these points, these blue X's? I use some criteria, and here's the important thing. I'm using a criteria that's based on the surrogate, right? It's not based on the simulator. And remember, surrogates are thrifty. They're quick to evaluate compared to my simulator. So doing this inner optimization is relatively quick compared to my actual optimization of the simulator. So the point surrounded by the white circle is what I choose to acquire, which is actually a pretty good observation. It's close to the minimum. I actually acquire it. When I mean say acquire, I mean I'm actually evaluating the simulator. So that's what takes a while to run. I acquire it, and here's another important part. I update my surrogate model to make it better, right? I'm improving the fidelity of it. And this is especially important when I'm starting out, is that I'm making my search better and better as I keep going along because my model gets better. Oh, sorry, last point. So this is just one run, right? So I want to repeat steps 3 through 6 until I converge, some metric of convergence, or in most cases, my budget runs out. I have some fixed number of evaluations I can do. Budget could be actual money or time, and that I just have until I need to say, okay, I'm done searching. Okay, I totally ignored this flutter requirement, right? So this is an example of constrained optimization, right? I have a constraint. So how do I deal with that? Well, it's nice because surrogates can also handle constraints. You can model the constraint just the same way you model an objective. So just an example, so I made this gray region also simulated to recommend that it shows the difference between valid and invalid designs. And what you can do is you can fit a surrogate using the same data that you're collecting to model the objective. You can train a model to estimate what the gray region looks like. And so this gray region is estimating the probability, whether the probability of satisfying the constraint is greater or less than 0.5, basically, as a decision rule. Okay, so there's one word in my presentation that I've neglected, which is robust. What makes a design robust? So flutter behavior depends on additional factors, right? So it depends on stuff like Mach number, so basically how fast the aircraft is moving. The structural damping coefficient is another kind of variable. And what's important is that these factors, or I call them like scenarios, they affect the feasibility of wing designs, right? And so what the problem is that what's feasible design versus infeasible can vary, right? So here's an example. So I show like when the Mach number is 0.1, imagine that this is what the constraint region looks like. Most of the designs are feasible. But as I increase the Mach number, the feasibility region gets smaller and smaller, right? So there are fewer feasible designs, which makes sense as the aircraft moves faster and faster. So kind of the idea of robustness that I'm defining here is that a robust design is feasible under a variety of scenarios, not just one or two. Okay, and so now what's this idea of robust design optimization? This is kind of like the new stuff, quote unquote. So one option, so rather than just evaluating it for one scenario, that would be something called a nominal design, I want to evaluate Flutter under a variety of different scenarios. So each different scenario, each Mach number and structural damping coefficient is going to give me a unique Flutter output. So now the question is, what does it mean now to satisfy the constraint? Right? It's now not just a binary thing. Now it's this kind of gradient. There are gradations of feasibility. Right? So the part of the region that's in the darkest color that doesn't satisfy the Flutter constraint for any Mach numbers, right? But as you get towards lighter and lighter colors, eventually to the white color, you're satisfying the Flutter constraint for more and more Mach numbers, right? So what we can do is we can kind of look at three different designs, right? This is an example of I would say not a robust design. It has a very small wing weight. It's very close to the minimum, but it only satisfies the Flutter constraint for one Mach number. Whereas a medium robust design satisfies, it's a little bit worse in terms of weight, right? There's a trade-off, but you're a little more robust in that there are more Mach numbers that you satisfy. And then finally, I would consider this the most robust design because every Mach number that I tried, it satisfied the Flutter constraint. So kind of the main idea, just to take away from this, is that I kind of have this knob that I can tune in terms of how robust I want. And I can use that in combination with my Bayesian optimization search to find what I consider, how robust of a design I want. I can do this multiple times and figure out, what the level of robustness I think is acceptable or what I want. And I think that's it. Thanks.